Learning objectives. In this chapter, the user will learn the following in detail: multiplying large integers, binary search, finding median, quick sort, matrix multiplication. Binary search. Binary search is the algorithm used to look up a word in a dictionary or a name in a telephone directory. It is probably the simplest application of divide and conquer. Let T of 1 to n be an array sorted into increasing order. That is, 1 less than or equal to I less than j less than or equal to n, and let x be some item. The problem consists of finding x in the array T if indeed it is there. If the item we are looking for is not in the array, then instead we want to find the position where it might be inserted. Formally, we wish to find the index I such that 0 less than or equal to I less than or equal to n, and T of I less than or equal to x less than T of I plus 1, with the logical convention that T of 0 equals negative infinity and T of n plus 1 equals positive infinity. The obvious approach to this problem is to look sequentially at each element of T until we either come to the end of the array or find an item bigger than x. Sequential function is shown in this figure. This algorithm clearly takes a time in theta of 1 plus r, where r is the index returned. This is big omega of n in the worst case and big O of 1 in the best case. If we assume that all the elements of T are distinct, that x is indeed somewhere in the array, and that it is to be found with equal probability each possible position, then the average number of trips round the loop is n square plus 3n minus 2 divided by 2n. On the average, therefore, as well as in the worst case, sequential search takes a time in theta of n. To speed up the search, divide and conquer suggests that we should look for x either in the first half of the array or in the second half of the array. To find out which of these searches is appropriate, we compare x to an element in the middle of the array. If x less than T of 1 plus floor of n by 2, then the search for x can be confined to T of 1 up to floor of n by 2. Otherwise, it is sufficient to search T of 1 plus floor of n by 2 up to n. We obtain the following algorithm. This algorithm in fact executes only one of the two recursive calls, so that technically it is an example of simplification rather than of divide and conquer. Because the recursive call is situated dynamically at the very end of the algorithm, it is easy to produce an iterative version. Iterative binary search procedure is shown in this figure. A first inspection of this algorithm shows what is apparently an inefficiency. Suppose T contains 17 distinct elements and that x equals T of 13. On the first trip round the loop, I equals 1, j equals 17 and k equals 9. The comparison between x and T of 9 causes the assignment I gets 9 to be executed. On the second trip round the loop, I equals 9, j equals 17 and k equals 13. A comparison is made between x and T of 13. This comparison would allow us to end the search immediately, but no test is made for equality, and so the assignment I gets 13 is carried out. 2 more trips round the loop are necessary before we leave with I equals j equals 13. This algorithm leaves the loop immediately after we find the element we are looking for. How binary search works? The sorted array is given below and assume that we need to search location of value 31 using binary search. First, we shall determine the half of the array by using this formula. Mid equals low plus high minus low by 2. Here it is 0 plus 9 minus 0 by 2 equals 4, integer value of 4.5. So 4 is the mid of array. Now we compare the value stored at location 4 with the value being searched, that is 31. We find that value at location 4 is 27, which is not a match. Because value is greater than 27 and we have a sorted array. So we also know that target value must be in upper portion of the array. We change our low to mid plus 1 and find the new mid value again. Low equals mid plus 1. Mid equals low plus high minus low by 2. Our new mid is 7 now. We compare the value stored at location 7 with our target value 31. The value stored at location 7 is not a match. Rather, it is less than what we are looking for. So the value must be in lower part from this location. So we calculate the mid again. This time it is 5. We compare the value stored at location 5 with our target value. We find that it is a match. We conclude that the target value 31 is stored at location 5. Binary search halves the searchable items and thus reduces the count of comparisons to be made to very less numbers. Which of these algorithms is better? The first systematically makes a number of trips round the loop in big O of log n, regardless of the position of x in t, while it is possible that the variant will only make 1 or 2 trips round the loop if x is favorably situated. On the other hand, a trip round the loop in the variant will take a little longer to execute on the average than a trip round the loop in the first algorithm. To compare them, we shall analyze exactly the average number of trips round the loop that each version makes. Suppose, to make life simpler, that T contains n distinct elements and that x is indeed somewhere in T, occupying each possible position with equal probability. Let A of n and B of n be the average number of trips round the loop made by the first and the second iterative versions, respectively. Analysis of the first version. Let k equals 1 plus flow of n by 2 with probability k minus 1 by n, x less than t of k, which causes the assignment j gets k minus 1, after which the algorithm starts over on an instance reduced to k minus 1 elements. With probability 1 minus k minus 1 by n, x greater than or equal to t of k, which causes the assignment I gets k, after which the algorithm starts over on an instance reduced to n minus k plus 1 elements. One trip round the loop is carried out before the algorithm starts over. So the average number of trips round the loop is given by the recurrence A of n equals 1 plus flow of n by 2 over n into A of flow of n by 2 plus ceiling of n by 2 over n into A of ceiling of n by 2, where n greater than or equal to 2. A of 1 equals 0. Analysis of the second version. In a similar way, taking k equals ceiling of n by 2, we obtain the recurrence B of n equals 1 plus ceiling of n by 2 minus 1 over n into B of ceiling of n by 2 minus 1 plus flow of n by 2 over n into B of flow of n by 2, where n greater than or equal to 3. B of 1 equals 0 and B of 2 equals 1. Define A of n and B of n as n a of n and n b of n respectively. The equations then become a of n equals n plus a of floor of n by 2 plus a of ceiling of n by 2 where n greater than or equal to 2. B of n equals n plus b of ceiling of n by 2 minus 1 plus b of floor of n by 2 where n greater than or equal to 3. A of 1 equals b of 1, it equals 0. B of 2 equals 2. The first equation is easy in the case when n is a power of 2, since it then reduces to a of n equals 2a of n by 2 plus n, where n greater than or equal to 2. A of 1 equals 0. Exact analysis for arbitrary n is harder. We proceed by constructive induction, guessing the likely form of the answer and determining the missing parameters in the course of a tentative proof by mathematical induction. A likely hypothesis already shown to hold when n is a power of 2 is that n flow of log n less than or equal to a of n less than or equal to n ceiling of log n. What might we add to n flow of log n to arrive at a of n? Let n star denote the largest power of 2 that is less than or equal to n. In particular, flow of log n equals log n star. It seems reasonable to hope that a of n equals n log n star plus cn plus dn star plus e log n star plus f for appropriate constants c, d, e and f. Denote this hypothesis by hi of n. When n greater than 1 is not of the form 2 power m minus 1, then flow of n by 2 the whole power star equals ceiling of n by 2 the whole power star equals n power star by 2. To prove hi of n, in this case using the recurrence star hi of flow of n by 2 and hi of ceiling of n by 2, it is thus necessary and sufficient that n log n star plus cn plus dn star plus e log n star plus f equals n log n star plus cn plus dn star plus 2e log n star plus 2f minus 2e. That is, we need e equals 0 and f equals 0, c and d being still unconstrained. If our hypothesis is correct, we therefore know a of n equals n log n star plus cn plus dn star. When n greater than 1 is of the form 2 power m minus 1, then flow of n by 2 equals n minus 1 by 2, comma, flow of n by 2 the whole power star equals n plus 1 by 4, and ceiling of n by 2 equals ceiling of n by 2 the whole power star equals n power star equals n plus 1 by 2. To prove hi of n, in this case, it is necessary and sufficient that which is shown in this figure. That is, 4c plus 2d equals 4c plus 3d plus 2 and 2d equals 3d plus 2. These two equations are not linearly independent. They allow us to conclude that d equals minus 2, there still being no constraints on c. At this point, we know that if only we can make the hypothesis a of n equals n log n star plus cn minus 2n star true for the base n equals 1, then we shall have proved by mathematical induction that it is true for every positive integer n. Our final constraint is therefore 0 equals a of 1 equals c minus 2, which gives c equals 2 and implies that the general solution of the recurrence star for a of n is a of n equals n log n star plus 2 of n minus n star. The average number of trips round the loop executed by the first iterative algorithm for binary searching, when looking for an element that is in fact present with uniform probability distribution among the n different elements of an array sorted into increasing order is given by A of n equals small a of n by n. That is, A of n equals flow of log n plus 2 into 1 minus n star over n. In particular, our initial guess holds flow of log n less than or equal to A of n less than or equal to ceiling of log n. The general solution of the recurrence for B of n is more difficult than the one we have just obtained. It seems reasonable to formulate the same incompletely specified induction hypothesis. B of n equals n log n star plus Cn plus dn star plus E log n star plus f for some new constants C, D, E and f. Constructive induction yields E equals 1 and f equals 1 plus C to take account of the case when n greater than or equal to 3 is not a power of 2. The case when n greater than or equal to 4 is a power of 2 obliges us to choose D equals minus 2. The hypothesis therefore becomes B of n equals n log n star plus Cn minus 2n star plus log n star plus 1 plus C. Unfortunately, B of 1 equals 0 implies C equals 1 by 2, whereas B of 2 equals 2 implies C equals 2 by 3, which is inconsistent and shows that the original hypothesis was wrong. The problem arises because the two basic cases are incompatible in the sense that it is impossible to obtain them both from the recurrence starting from some artificial definition of B of 0. Nonetheless, our efforts were not entirely in vain. A simple modification of the argument allows us to conclude that as follows. Which of the two algorithms for binary searching is preferable? We obtain the following result. Thus, we see that the first algorithm makes on the average less than 1.5 trips round the loop more than the second. Given that the first algorithm takes less time on the average than the variant to execute one trip round the loop, we conclude that the first algorithm is more efficient than the second on the average whenever n is sufficiently large. The situation is similar if the element we are looking for is not in fact in the array. However, the threshold beyond which the first algorithm is preferable to the variant can be very high for some implementations. Finding median. Median finding algorithm is also called as linear time selection algorithm. The selection problem requires us to find the kth smallest element in a collection S of n elements. It is the special case of finding the median. This occurs when k equals ceiling of n by 2. Although this algorithm runs in linear average time, it has a worst case of big O of n square. Selection can easily be solved in big O of n log n, worst case time by sorting the elements, but for a long time it was unknown. The basic algorithm is a simple recursive strategy. Assuming that n is larger than the cutoff point where elements are simply sorted, and element v, known as the pivot, is chosen. The remaining elements are placed into two sets, S1 and S2. S1 contains elements that are guaranteed to be no larger than v, and S2 contains elements that are no smaller than v. Finally, if k less than or equal to modulus of S1, then the kth smallest element in S can be found by recursively computing the kth smallest element in S1. If k equals modulus of S1 plus 1, then the pivot is the kth smallest element. Otherwise, the kth smallest element in S is the k minus modulus of S1 minus 1st smallest element in S2. The main difference between this algorithm and quicksort is that there is only one subproblem to solve instead of two. In order to obtain a linear algorithm, we must ensure that the subproblem is only a fraction of the original and not merely only a few elements smaller than the original. Of course, we can always find such an element if we are willing to spend some time to do so. The difficult problem is that we cannot spend too much time finding the pivot. For quicksort, we saw that a good choice for pivot was to pick 3 elements and use their median. This gives some expectation that the pivot is not too bad but doesn't provide a guarantee. We should choose 21 elements at random, sort them in constant time, use the 11th largest as pivot, and get a pivot that is even more likely to be good. However, if these 21 elements were the 21 largest, then the pivot would still be poor. Extending this, we would use up to big O of n by log n elements. Sort them using heap sort in big O of n total time and be almost certain from a statistical point of view of obtaining a good pivot. In the worst case, however, this does not work because we might select the big O of n by log n largest elements, and then the pivot would be the n minus big O of n by log nth largest element, which is not a constant fraction of n. The basic idea is still useful. Indeed, we will see that we can use it to improve the expected number of comparisons that quick select makes. To get a good worst case, however, the key idea is to use one more level of indirection. Instead of finding the median from a sample of random elements, we will find the median from a sample of medians. The basic pivot selection algorithm. Step 1. Arrange the n elements into n by 5 groups of 5 elements, ignoring the at most 4 extra elements. Step 2. Find the median of each group. This gives a list M of n by 5 medians. Step 3. Find the median of M. Written this as the pivot V. Median of 5 partitioning. Used to describe the quick select algorithm that uses the pivot selection rule. We will show that median of 5 partitioning guarantees that each recursive subproblem is at most roughly 70% as large as the original. We will also show that the pivot can be computed quickly enough to guarantee an big O of n running time for the entire selection algorithm. Let us assume for the moment that n is divisible by 5, so there are no extra elements. Suppose also that n by 5 is odd, so that the set M contains an odd number of elements. This provides some symmetry. Assuming, for convenience, that n is of the form 10k plus 5 and that all the elements are distinct, the actual algorithm must make sure to handle the case where this is not true. This figure shows how the pivot might be chosen when n equals 45. From this figure, V represents the element which is selected by the algorithm as pivot. Since V is the median of 9 elements and we are assuming that all elements are distinct, there must be 4 medians that are larger than V and 4 that are smaller. We denote these by L and S respectively. Consider a group of 5 elements with a large median, type L. The median of the group is smaller than 2 elements in the group and larger than 2 elements in the group. Let H represent the huge elements. These are elements that are known to be larger than a large median. Similarly, T represents the tiny elements which are smaller than a small median. There are 10 elements of type H. 2 are in each of the groups with an L-type median and 2 elements are in the same group as V. Similarly, there are 10 elements of type T. Elements of type L or H are guaranteed to be larger than V, and elements of type S or T are guaranteed to be smaller than V. There are thus guaranteed to be 14 large and 14 small elements in our problem. Therefore, a recursive call could be on at most 45 minus 14 minus 1 equals 30 elements. Let us extend this analysis to general n of the form 10k plus 5. In this case, there are k elements of type L and k elements of type S. There are 2k plus 2 elements of type H and also 2k plus 2 elements of type T. Thus, there are 3k plus 2 elements that are guaranteed to be larger than V and 3k plus 2 elements that are guaranteed to be smaller. Thus, in this case, the recursive call can contain at most 7k plus 2 less than 0.7 n elements. If n is not of the form 10k plus 5, similar arguments can be made without affecting the basic result. It remains to bound the running time to obtain the pivot element. There are 2 basic steps. We can find the median of 5 elements in constant time. For instance, it is not hard to sort 5 elements in 8 comparisons. We must do this n by 5 times. So this step takes big O of n time. We must then compute the median of a group of n by 5 elements. The obvious way to do this is to sort the group and return the element in the middle. But this takes big O of n by 5 log n by 5 equals big O of n log n time. So this does not work. The solution is to call the selection algorithm recursively on the n by 5 elements. This completes the description of the basic algorithm. There are still some details that need to be filled in if an actual implementation is desired. For instance, duplicates must be handled correctly, and the algorithm needs a cutoff large enough to ensure that the recursive calls make progress. There is quite a large amount of overhead involved and this algorithm is not practical at all. Example of finding median. Arrange the numbers in groups of 5 is shown in this figure. Find median of n by 5 groups is shown in this figure. Find the median of each group is shown in this figure. Find the sets L and R. Compare each n-1 elements with the median m and find 2 sets L and R such that every element in L is smaller than m and every element in R is greater than m. If n is small, for example n less than 6, just sort and return the k, the smallest number. Bound time is 7. If n greater than 5, then partition the numbers into group of 5. Bound time is n by 5. Sort the numbers within each group. Select the middle elements, the medians. Bound time is 7n by 5. Call your selection routine recursively to find the median of n by 5 medians and call it m. Bound time is tn by 5. Compare all n-1 elements with the median of medians m and determine the sets L and R, where L contains all elements less than m and R contains all elements greater than m. Clearly, the rank of m is R equals modulus of L plus 1. Modulus of L is the size or cardinality of L. Bound time is n. If k equals R, then return m. If k less than R, then return kth smallest of the set L. Bound time is T7n by 10. If k greater than R, then return k minus rth smallest of the set R. Recursive formula for group of 5. T of n equals big O of n plus T of n by 5 plus T of 7n by 10. We will solve this equation in order to get the complexity. We assume that T of n as follows. There is such a constant that exists, so T of n equals big O of n. We can try some other groups. For example, if we divide elements into groups of 3, then the recursive formula will be T of n equals big O of n plus T of n by 3 plus T of 2n by 3. So T of n greater than big O of n. If we divide elements into groups of more than 5, the value of constant 5 will be more. So grouping elements into 5 is the optimal situation. Reducing the average number of comparisons. Divide and conquer can also be used to reduce the expected number of comparisons required by the selection algorithm. Let us look at a concrete example. Suppose we have a group S of 1000 numbers and are looking for the 100th smallest number, which we will call X. We choose a subset S of S consisting of 100 numbers. We would expect that the value of X is similar in size to the 10th smallest number in S dash. More specifically, the 5th smallest number in S dash is almost certainly less than X, and the 15th smallest number in S dash is almost certainly greater than X. More generally, a sample S of S elements is chosen from the n elements. Let delta be some number which we will choose later so as to minimize the average number of comparisons used by the procedure. We find the V1 equals Ks by n minus delta and V2 equals Ks by n plus delta smallest elements in S dash. Almost certainly, the kth smallest element in S will fall between V1 and V2, so we are left with a selection problem on 2 delta elements. With low probability, the kth smallest element does not fall in this range, and we have considerable work to do. However, with a good choice of S and delta, we can ensure by the loss of probability that the second case does not adversely affect the total work. If an analysis is performed, we find that if S equals n power 2 by 3 log power 1 by 3 n and delta equals n power 1 by 3 log power 2 by 3 n, then the expected number of comparisons in n plus k plus big O of n power 2 by 3 log power 1 by 3 n, which is optimal except for the lower order term. If k greater than n by 2, we can consider the symmetric problem of finding the n minus kth largest element. The last term represents the cost of performing the two selections to determine V1 and V2. The average cost of the partitioning, assuming a reasonably clever strategy, is equal to n plus the expected rank of V2 in S, which is n plus k plus big O of n delta by S. If the kth element wins up in S dash, the cost of finishing the algorithm is equal to the cost of selection on S dash, namely big O of S. If the kth smallest element doesn't wind up in S dash, the cost is big O of n. However, S and delta have been chosen to guarantee that this happens with very low probability small o of 1 by n. So, the expected cost of this possibility is small o of 1, which is a term that goes to 0 as n gets large. This analysis shows that finding the median requires about 1.5 n comparisons on average. Of course, this algorithm requires some floating point arithmetic to compute S, which can slow down the algorithm on some machines. Matrix multiplication. A fundamental numerical problem is the multiplication of two matrices. This figure gives a simple big O of n cube algorithm to compute C equals AB, where A, B and C are n by n matrices. The algorithm follows directly from the definition of matrix multiplication. To compute C, I, j, we compute the dot product of the ith row in A with the jth column in B. As usual, arrays begin at index 0. For a long time, it was assumed that big omega of n cube was required for matrix multiplication. However, in the late 60s, Strawson showed how to break the big omega of n cube barrier. The basic idea of Strawson's algorithm is to divide each matrix into 4 quadrants as shown in this figure. Then it is easy to show that as follows. As an example, to perform the multiplication of A and B, which is shown below, we define the following 8 n by 2 by n by 2 matrices, as shown here. Then perform 8 n by 2 by n by 2 matrix multiplications and 4 n by 2 by n by 2 matrix additions. The matrix additions take big O of n square time. If the matrix multiplications are done recursively, then the running time satisfies T of n equals 8T of n by 2 plus big O of n square. Multiplying large integers. A divide and conquer algorithm that multiplies two n-digit numbers. If we measure multiplication in terms of the size of numbers being multiplied, then the natural multiplication algorithm takes quadratic time. The divide and conquer algorithm runs in subquadratic time. The classic divide and conquer algorithm that multiplies two n by n matrices in subcubic time. Multiplying integers. To multiply two n-digit numbers x and y, if exactly one of x and y is negative, then the answer is negative. Otherwise, it is positive. Perform this check and then assume that x, y greater than or equal to 0. The algorithm that almost everyone uses when multiplying by hand requires n square operations because each digit in x is multiplied by each digit in y. If x equals 61, 438, 521 and y equals 94, 736, 407, xy equals 5, 820, 464, 730, 934, 047. Let us break x and y into two halves consisting of the most significant and least significant digits respectively. Then xl equals 6, 143, xr equals 8, 521, yl equals 9, 473 and yr equals 6, 407. We also have x equals xl 10 power 4 plus xr and y equals yl 10 power 4 plus yr. It follows that xy equals xl yl 10 power 8 plus xlyr plus xryl into 10 power 4 plus xryr. This equation consists of 4 multiplications xlyl, xlyr, xryl and xryr, which are each half the size of the original problem, n by 2 digits. The multiplications by 10 power 8 and 10 power 4 amount to the placing of zeros. This and the subsequent additions add only big O of n additional work. If we perform these four multiplications recursively using this algorithm, stopping at an appropriate base case, then we obtain the recurrence T of n equals 4T of n by 2 plus big O of n. To achieve a subquadratic algorithm, we must use less than 4 recursive calls. The key observation is that XL YR plus XR YL equals XL minus XR YR minus YL plus XL YL plus XR YR. Thus, instead of using two multiplications to compute the coefficient of 10 power 4, we can use one multiplication plus the result of two multiplications that have already been performed. This figure shows how only 3 recursive subproblems need to be solved. It is easy to see that now the recurrence equation satisfies T of n equals 3T of n by 2 plus big O of n. And so, we obtain T of n equals big O of n power log 3 base 2 equals big O of n power 1.59. To complete the algorithm, we must have a base case which can be solved without recursion. When both numbers are one digit, we can do the multiplication by table lookup. If one number has 0 digits, then we return 0. In practice, if we were to use this algorithm, we would choose the base case to be that which is most convenient for the machine. Although this algorithm has better asymptotic performance than the standard quadratic algorithm, it is rarely used because for small n, the overhead is significant, and for larger n, there are even better algorithms. These algorithms also make extensive use of divide and conquer. This figure shows divide and conquer integer multiplication algorithm. Note that the lines 8 to 11 of this algorithm are performed by copying bits and the multiplication by 2 power n and 2 power n by 2 in line 16 by shifting. Also, the multiplication by s in line 16 simply introduces the proper sign into the result. Quicksort. Quicksort algorithm is most efficient for internal sorting. Quicksort is sort an array A of 1 to A of n by picking some key value v in the array as a pivot element. Although there are many different ways to choose the pivot value, we will simply use the first item in the list. The role of the pivot value is to assist with splitting the list. The actual position where the pivot value belongs in the final sorted list, commonly called the split point, will be used to divide the list for subsequent calls to the quicksort. The pivot is near the median key value in the array, so that it is preceded by about half the keys and followed by about half the keys. Permute the elements in the array so that for some j, all the records with keys less than v appear in A of 1 to A of j, and all those with keys v or greater appear in A of j plus 1 to A of n. Then apply quicksort recursively to A of 1 to A of j and to A of j plus 1 to A of n to sort both these groups of elements. Since all keys in the first group precede all keys in the second group, the entire array will thus be sorted. Let us now begin the design of a recursive procedure quicksort of I, j that operates on an array A with elements A of 1 to A of n defined externally to the procedure. Quicksort of I, j sorts A of I through A of j in place. The following figure shows a preliminary sketch of the quicksort procedure. Note that if A of I to A of j all have the same key, the procedure does nothing to A. We begin by developing a function findPivot that implements the test of line 1 of this algorithm, determining whether the keys of A of I to A of j are all the same. If findPivot never finds two different keys, it returns 0. Otherwise, it returns the index of the larger of the first two different keys. This larger key becomes the pivot element. The function findPivot is shown in this figure. Next, we implement line 3 of the sketch of the quicksort procedure, where we face the problem of permuting A of I to A of j, so that all the keys smaller than the pivot value appear to the left of the others. To do this task, we introduce two cursors L and R, initially at the left and right ends of the portion of A being sorted respectively. At all times, the elements to the left of L, that is A of I to A of L minus 1, will have keys less than the pivot. Elements to the right side of R, that is A of R plus 1 to A of j, will have keys equal to or greater than the pivot, and elements in the middle will be mixed as suggested in this figure. Initially, I equal to L and j equal to R. So the above statement holds since nothing is to the left of L or to the right of R. We repeatedly do the following steps, which move L right and R left until they finally cross, whereupon A of I to A of L minus 1 will contain all the keys less than the pivot, and A of R plus 1 to A of j all the keys equal to or greater than the pivot. Scan. Move L right over any records with keys less than the pivot. Move R left over any keys greater than or equal to the pivot. Note that our selection of the pivot by findPivot guarantees that there is at least one key less than the pivot and at least one not less than the pivot. So L and R will surely come to rest before moving outside the range I to j. Test. If L greater than R, which is practice means L equals R plus 1, then we have successfully partitioned A of I to A of j and we are done. Switch. If L less than R, note we cannot come to rest during the scan with L equals R, because one or the other of these will move past any given key. Then swap of A of L with A of R. After doing so, A of L has a key less than the pivot and A of R has a key at least equal to the pivot. So, we know that in the next scan phase, L will move at least one position right over the old A of R, and R will move at least one position left. The above loop is awkward since the test that terminates it is in the middle. To put it in the form of a repeat loop, we move the switch phase to the beginning. The effect is that initially, when I equal to L and j equal to R, we shall swap A of I with A of j. This would be right or wrong. It doesn't matter, as we assume no particular order for the keys among A of I to A of j initially. The reader, however, should be aware of this trick and not be puzzled by it. The function partition is shown in this figure, which performs the above operations and returns L, the point at which the upper half of the partitioned array begins. We are now ready to elaborate the quicksort sketch. The final program is shown in this figure. To sort an array A of type array of 1 to n of record type, we simply call quicksort of 1, n. Example of quicksort. This figure shows that 54 will serve as our first pivot value. Finding the split point for 54. The partition process will start next. It will find the split point and at the same time move other items to the appropriate side of the list, either less than or greater than the pivot value. Partitioning begins by locating two pointer positions. Let's mark them as L, left side pointer, at the beginning of the list, and R, right side pointer, at the end of the list. The goal of the partition process is to move items that are on the wrong side with respect to the pivot value while also converging on the split point. This figure shows L and R will converge on split point. Begin by incrementing left side pointer until we locate a value that is greater than the pivot value. Then decrement right side pointer until we find a value that is less than the pivot value. At this point, we have discovered two items that are out of place with respect to the eventual split point. In this example, it occurs at 93 and 20. Now we can exchange these two items and then repeat the process again. In this figure, 26 less than 54, so move right, and 93 greater than 54, so stop there. Now check the R right side pointer value 20 less than 54 and swap 20 and 93. Now continue moving L and R. 77 greater than 54, so stop the left pointer. 44 less than 54, so stop the right pointer. Then swap 77 and 44. At the point when the right side pointer becomes less than left side pointer, then stop the process. The position of right side pointer is now the split point. In this figure, 77 greater than 54, so stop there. 31 less than 54, so stop there. Or less than L found, so swap 54 and 31. The pivot value can be exchanged with the contents of the split point and the pivot value is now in place. In addition, all the items to the left of the split point are less than the pivot value, and all the items to the right of the split point are greater than the pivot value. Now the list can be divided at the split point, and the quick sort can be invoked recursively on the two halves. In this figure shows the 54 is in place. Left half side values are less than 54 and right half side values are greater than 54. The left half and right half of the quicksort is shown in this figure. The running time of quicksort. We shall show that quicksort takes big O of n log n time and the average to sort n elements and big O of n square time in the worst case. The first step in the substantiating both claims is to prove that partition takes time proportional to the number of elements that it is called upon to separate, that is, big O of j minus I plus 1 time. To see why that statement is true, we must use a trick that comes up frequently in analyzing algorithms. We must find certain items to which time may be charged, and then show how to charge each step of the algorithm so no item is charged more than some constant. Then the total time spent is no greater than this constant times the number of items. In this case, the items are the elements from Ai to Aj, and we charge to each element all the item spent by partition from the time L or R. First points to that element to the item L or R leaves that element. First, note that neither L nor R ever returns to an element, because there is at least one element in the low group and one is the high group, and partition stops as soon as L exceeds R. Each element will be charged at most once. We move off an element in the loops of lines 4 and 6 of the partition procedure either by increasing L or decreasing R. how long would it be between times when we execute L equals L plus 1 or R equals R minus 1? Lines 1 and 2 initialize L and R. Then we might go around the loop without doing anything to L or R. On the second and subsequent passes, the swap at line 3 guarantees that while loops of lines 4 and 6 will be successful at least once each. So the worst that can be charged to an execution of L equals L plus 1 or R equals R minus 1 is the cost of line 1, line 2, twice line 3 and the tests of lines 4, 6, 8 and 4 again. This is only a constant amount independent of I or j, and subsequent execution of L equals L plus 1 or R equals R minus 1 are charged less, at most one execution of lines 3 and 8 and once around the loops of lines 4 or 6. There are also the final 2 unsuccessful tests at lines 4, 6 and 8 that may not be charged to any item, but these represent only a constant amount and may be charged to any item. After all charges have been made, we still have some constant C so that no item has been charged more than C time units. Since there are j minus I plus 1 items, that is, elements in the portion of the array to be sorted, the total time spent by partition of I, j, pivot is big O of j minus I plus 1. Let us turn to the running time spent by quicksort of I, j. Easily check that the time spent by the call to find pivot at line 1 of quicksort procedure, shown in this figure, is big O of j minus I plus 1 and in most cases much smaller. The test of line 2 takes a constant amount of time, as does step 3 if executed. Line 4, the call to partition, will take big O of j minus I plus 1 time. Thus, exclusive of recursive calls it makes to quicksort. Each individual call of quicksort takes time at most proportional number of elements it is called upon to sort. The total time taken by quicksort is the sum over all elements of the number of times that element is part of the subarray on which a call to quicksort is made, shown in this figure. Conclusion. In this chapter, we have covered the following in detail: multiplying large integers, binary search, finding median, quicksort, matrix multiplication.